Hello friends, welcome to my YouTube channel. Today we'll see another example of modeling flow through porous media. This tutorial illustrates how to set up and solve a problem involving gas flow through porous media. Catalytic converters are commonly used to purify emissions from gasoline and diesel engines by converting environmentally hazardous exhaust emission to acceptable substances. Example of such emission include carbon monoxide, nitrogen oxide, and unburned hydrocarbon fuels. These exhaust gas emissions are forced through a substrate which is a ceramic structure coated with a metal catalyst such as platinum or palladium. The nature of the exhaust gas flow is a very important factor in determining the performance of the catalytic converter. Of particular importance is the pressure gradient and velocity distribution through the substrate. This tutorial demonstrates how to do following: set up a porous zone for the substrate with appropriate resistance, calculate a solution for a gas flow through the catalytic converter using pressure-based solver. We will also plot pressure and velocity distribution on a specified plane of the geometry. Determine the pressure drop through the substrate and degree of non-uniformity of flow through cross-section of the geometry using XY plot and numerical reports. I have created a model in Creo. Actually, it is a assembly of three parts, where center portion is our substrate, that is a porous media, and bottom and front side we have the pipe which carry the flow. Here we have specified the dimension for this entire geometry, where the upper portion is showing the length of the model, and below portion showing the diameter. So here for substrate we have the 100 mm diameter, and for the pipe we have 15 mm diameter. Next we have to define the inlet, outlet, and wall. So here you can see we have one inlet and one outlet, and the pipe portion is our wall. So these two pipe we have the wall, and the center part is our substrate. So in the substrate again we have the inlet and outlet, so we call it is a porous in and porous out, and the rest of the portion is the substrate wall. Below a snap showing the proposed meshing. We will see the problem description. While the flow in the inlet and outlet section is turbulent, and the flow through the substrate is a laminar and should be laminar, and is characterized by the inertial and viscous loss coefficient along inlet axis. The substrate is a resistance in other direction, and this characteristics is modeled using the loss coefficients that are 3 order of magnitude higher than in main flow direction. As earlier I have mentioned that you will get this value from the supplier, and this value in 3 direction is far greater than the main flow direction. So let's get start with the Ansys Fluent. First we will call the geometry in project schematic. So just drag and drop here, just right click and import the geometry. As I mentioned earlier that I have created geometry in Creo. Again right click and open in design modular. You can also open in a space clip, but I am more comfortable with the design modular. It will take time to open in design modular. Yeah, now you can click on the generate to see the geometry. In the view you can also hide deselect the frozen body transparency if you want. Change the unit in millimeter. Okay, as I mentioned that this is the assembly and we have three parts. So first we'll rename these parts. So it is our front pipe, this is our substrate, and this is the back pipe. Yes, now we are to define the inlet outlet wall. So as we have seen that accordingly we are to define. So first we will define the inlet outlet wall of two pipes, then we'll move to the porous media. So just select the face from the selection filter and just click right click and name selection, say wall pipe wall 1, generate. Pipe wall 2, generate. Now just rotate, and this is our inlet. This will be our outlet. Okay, now this is our wall for substrate. Okay, now we are to define the inlet and outlet for substrate, and for that I will hide these two pipes, front pipe and back pipe, hide it. So here now you can see this portion is our inlet, porous, and this is our outlet for porous. Yes, once it is done, unhide the geometry. Now you can see this is the inlet, this is the outlet, then this is the pipe wall 2, then wall substrate. Again here we have defined, if I hide this again, now you can see inlet porous, and this is the outlet. Okay, so we have done with the geometry design modular. Now we'll move to the meshing. Just save your project. Now we'll attach the mesh with the geometry. Double click on mesh. It will take time to open the mesh module. Yeah, in the geometry now you can see we have front pipe, substrate and back pipe. In the mesh, first we will change the physics preference mechanical to CFD. Then in the sizing, we will change curvature to proximity and curvature. Relevance center should be fine, and transition should be slow. Okay, once it is done, just click on the mesh and generate mesh. First we will try with the automatic mesh, and after that we'll change. Now you can see it look good. Now it is structured mesh, and but still we will do some fine meshing here. So as you know that we have the diameter 100 and minimum diameter of pipe is 50 mm. So based on that we will do the meshing for that, and now we will do the sizing. uh, just go and select the edge. So here now select the all edges of the pipe and substrate, and in the type element size we will use the number of division instead of sizing. So we know the diameter 50, so we will divide that in a number of division. So we'll say 50, so we have the division of 11 mm, and just generate the mesh. Yes, now you can see we have the fine mesh than earlier. You can also check the quality of the meshing in the quality. Here you can check the mesh matrix with the orthogonal quality. In the console it will show the details. Now you can see here hex 8, and here edges it's showing. So now you can see the graph showing the maximum node is in near to 1, so it is good quality, we can say. Below 0.5 mm that we have to rectify. So we have done with the meshing. Now we will move to the setup. Before that, just save the project. Now we'll set up the model. Add a Fluent to mesh. Just update the mesh. It will take time because we have a very fine mesh. Yes, now it is done. Just double click on setup. Yes, now we'll go with the double precision and say OK. In the general setting, we'll go with the pressure based solver. Then yeah, it is a steady state simulation, not a transient. Okay, in the unit we'll change the velocity Yeah, now it is a meter per second, it is okay. Next, we have to define the model for this problem. As we have seen in the problem description that at initial stage it is a turbulent at in both the pipe, so we have to use the turbulent model for same. So just click on the this viscous laminar and select the K epsilon with the standard model, and near wall treatment we will keep the standard wall function as it is. Say okay. Now we have to add the material, so we'll add a material. We need a nitrogen for that, so we'll just click on the Fluent database. In the list of the material, click on nitrogen. Nitrogen, yes, nitrogen N2, and copy, create, close it. Okay. Next step is we have to define the fluid zone. That is the most important step. So in the cell zone, now you can see we have the three: back pipe, front pipe, or subset. So here we have to define. First we will define the back pipe. Instead of air, just the material name change to the nitrogen, and okay. Same for the front pipe, it is a nitrogen, and for the substrate, uh, it is a nitrogen, and we have to click on this porous zone here, and we have to fill the value for porous zone. So in the x, in the direction vector, go to the porous zone, and the direction vector we have to define the direction. That is as per our model, we have geometry in x directions, so here we will put a 1, and in the y it is 1, and for z it is 0. Also we have to set the value for same, so here we will define our value as I mentioned earlier, that this value should be higher or far greater than the flow direction. So here we will mention 3.846 e raised to 8. It is the same for 3 direction, 3.846 e raised to 8, 3.846. Okay. And now you can see here again, this is the viscous resistance for the porous media. This value you will get from the supplier, and here again we have to define the inertial resistance in the direction 1 2 3. Now here we have to define 20.6, 20.6 and 20.6. okay, now porosity should be 1, and now yes, we have defined the porous zone here. Say okay. Yes, now next is the boundary condition, and in the boundary conditions we have to define inlet that we have mentioned here. Now you can see here we have so many region. So just select the inlet, double click, and here velocity specification method is magnitude normal to boundary conditions, and magnitude here will use 25 meter per second, and turbulent intensity is 10, and here you can change to the hydraulic diameter intensity and hydraulic diameter, and turbulent intensity is 10, and the hydraulic diameter which is given on our geometry, here we have the pipe diameter 50 mm, so we'll put that here. Yes, and for the outlet we'll keep as it is, the pressure outlet, and again we have to change here intensity, hydraulic diameter. So here we will change with 5 intensity, and diameter is here. Now you can notice that diameter showing in a meter. Okay, so that we have to convert in a meter. So as you know that we have the 50 mm, so divided by 1000, so it should be 0.05 mm. 0.05, so it is in meter. So same we will change in the inlet also, or otherwise you have to change the unit. So we have defined our boundary conditions. Now we'll go with the solution method. In the reference value you can select the inlet. So here we have already defined, so all this value will come automatically here, the material density, area, then length, and temperature, velocity that we have defined. In the method we'll go to the coupled, and keep the rest of the option as it is, and just click on the pseudo transient, and yes, now just we'll create a surface monitor for that, and go to the report definitions and create a new surface report for the mass flow rate, and here we'll give the name surface monitor 1, and we'll look the mass flow rate at outlet. So select the outlet, and you can also use just click on the report file, and report plot on frequency should be 1, then print to console. Okay, yeah, now say OK. Then we'll go to the initialization, and here we'll go with the standard initialization. The reason is that standard is the recommended initialization method for the porous media simulation. The default hybrid method does not account for the porous media property, and depending on the boundary condition may produce a unrealistic initial velocity field for the porous media simulations. The hybrid method should only be used when the maintain a constant velocity magnitude option is enabled in the hybrid initialization dialog box. So we'll go with the standard, and reference frame is related to cell zone, and we'll compute again from the inlet. So we have all this value here. Now click on the initialization, initialize. Yeah, now you can see here, and just first save the right, auto save for the every 2 iterations. Okay, and now we will solve. Just in the run, put the number of iteration 100. We expect solution should be converged near about 60 to 70 iterations, and now calculate. So it will take time. I will come back once it is completed. Welcome back. Now you can see calculation completed, and the solution is converged at nearby 54 iteration after. And now if we see the surface monitor, here now you can see surface monitor, uh, the mass flow rate monitor flattened out as seen after 20. Okay, now we'll save this again. Okay, and now we will go with the post processing, and we will create a surface passing through the center line for post processing purpose. We will go to the post processing, create ISO surface, we will call mesh for the y coordinate. Here we will compute. Now as per our geometry, we have the minimum and maximum distance in a y direction, that is a 50 mm. So at center we will create a one plane. So here we will put a 0, and we will give the name y is equal to 0, and we will create 1. Same we have to create for substrate. We will create a 3 plane inlet in middle of substrate and outlet at substrate. So again, but in the x direction. So here again you can compute. Now we have the total length 0 to 375 mm. So if I recall the geometry, we have to create one surface here at inlet, then one at middle and one at outlet of the substrate. So this length is 75 plus 50 mm, so it is 125. Then in middle it is 125 plus 62.5 means 187.5 mm, and at outlet it is a 250. This is 125 and this is 125, so it is 250. So we will create 3 plane in x direction. So first is at 125 mm, 125 mm, and we'll give the name x is equal to 125. Create the same 187.5 mm, x is equal to 187.5. We'll create, and the third is 220, 250, x is equal to 250. So we have created plane. Then next is we'll create a line or rake, which is a center line for the porous media, and x is equal to 0, x0 is equal to 125, and x1 is equal to 250. If we again see, this is the 125 from here, and for here 250. So this is the x1 and this is the x2. So here we have to make a center plane, and the rest of the uh, dimension will be 0, and we'll give the name porous center line create, and we'll go to the post processing and mesh. We'll create a new and just deselect the edge and only select the pipe wall 2 and pipe wall 1 and wall substrate, and we'll give the name for that. We'll keep as it is, mesh 3, and display. And now you can see we have the geometry here, but we'll go to the viewing option. Just deselect this double buffer and keep light on and apply. After that we'll go to the scene for the transparency purpose, and here select the mesh 3, which is created right now, just now, and here we'll set the transparency. Now you can see, okay, and here we'll call a vector. We'll create a vector, vector velocity, that we'll see the vector velocity at y is equal to 0, and we'll call the draw mesh display. Now go to the scene 1, and already we have selected mesh 3 and transparency is 75. Select the vector velocity. Now you can see at the center of the porous media we have the plane, and we have plotted the vector contour there. Now you can see the flow pattern show that the flow enters the catalytic converter as a jet with recirculation on either side of the jet. There is little bit of recirculation, and it passes through the porous substrate then here, and it decreases and decreases, and a more uniform velocity distribution you can see in porous media. So this is our laminar flow actually, and again at outlet we have the turbulent flow. Now we will see the pressure. Again we will create a contour for the, you can select phase and pressure, static pressure, and display it. We'll deselect the velocity vector, and we'll select the contour and display. Now you can see here static pressure across the surface of center line of the porous media. Next, we'll plot a static pressure on the porous center line surface, and for that, before that, we'll see the contour, velocity contour. Velocity contour, and which is for the surfaces. We have created 3 surfaces. Just select and display. Just deselect the global range. You will have the correct distributions, and now again deselect this contour 1 and contour 2. Here you can see the velocity profile become more uniform as the fluid passes through the porous media, and the velocity is very high at the center of the center area and just before the nitrogen enters the substrate. So at inlet of the substrate we have the maximum velocity or very high velocity at center area, and the substrate, and then decreases as it passes through the center, and the area in a green, which correspond to the moderate velocity, increases in extent. So also we'll plot. Now we'll go to the post processing and we'll plot new xy plot at center line, that is our porous center line, and here we'll use the pressure and static pressure and just plot it. Now you can see, you can also go to the curve and change the symbol to dash and again plot it. Now you can see the pressure drop across the porous substrate is approximately 200, we can say. If we compare this here we have 1000, so we assume that it is a 200, 400, 600, 800, like that. So pressure is dropped when it enters from the porous media. Next we'll see the surface integral. For that we'll go to the reports and we'll go to the surface integral, and we'll see the mass weighted average in velocity and choose the x velocity. We have to see in x direction, and for that we will select a two plane, that is the one middle plane and outlet of porous media, and we'll compute. So it's showing the 6.25 meter per second at that locations. Also you can go and select the facet minimum, so it will showing the minimum at that location. It is a 560. In console you can also check x is equal to 187.5. we have the maximum and a minimum at 250. Also you can go to the facet maximum, and if you check on the console, so this is the mass weighted average and x velocity at the location of 187 and 250 mm. So accordingly, so it's the spread between the average maximum and minimum value of x velocity gives the degree to which the velocity distribution is non uniform. You can also use this number to calculate the velocity ratio using the custom UDF. So in this tutorial we have solved the problem involving the gas flow through the porous media, and for the further improvement you can go through the step to reach initial solution, and you may be able to obtain a more accurate solution by using appropriate higher order discretization scheme and adopting mesh. So if you like this video, please press the like button and subscribe my channel. In next video or a tutorial we will see the another example of the porous media. Thank you very much for your